Okay. Yeah, sorry about any delay before the lecture. I have like a few minutes to set up my laptops and tablets and stuff going on here. All right, so announcement, the homework 1, the solution has been posted, and homework 2 has been posted. So I will post the solution for the homework 2 a little bit earlier than this one. Probably you will see the solution like during the weekend, I'll say Saturday. So you can just prepare the quizzes first. So quizzes is not going to be, that hard. Okay, I just want you to look at I emphasize a lot of the assumptions, right? When I just write the equation, write down the equation. So I just want to check if you just understand what the equation you adopt for the specific situation for the flow field, and things like that. So it's going to be probably half of them going to be just a multi-choice choice problems, and just 1 or 2 you might need to write down some equation and solve it. It's not going to be that difficult. This is quizzes, so. All right, I'll just talk about it more details next week. And for the lab, I'll just keep the first lab as a synchronous online lab. So I will just turn the teams like that, schedule the teams, and you'll just hop into the teams. And I'm going to just give you a short kind of lectures with a lab handout, which will shoot out like today afternoon, I guess. Then you guys can just jump in on the lab, or you can just do it during the weekend. That's fine. You will have a week from now to submit your answers. I will just give it a bunch of questions at this point. It's not going to be the lab report format, but I think the second lab you might need to submit the form of the report with several list of the deliverables. Okay, so I think the section 11 should be on Thursday, 1 a.m. So I'll start at 1. And section 12 is on Friday. So I'll just hold all the lab based on the schedule this time. And from the next week, it's going to be recorded video, and I'll just open my Teams for the office hour. Okay, any questions? So let's go back to here. So this is what we have yesterday. So let's just copy that. Yeah, it's huge. Okay. So now it's time to plug the boundary condition. So we still have a same setup. We have 2 infinite plates up and down, up and bottom, top and bottom. Then it's fixed at its location, and flow is a fully developed and steady state. Then it is incompressible Newtonian fluids. So then it's time for the boundary condition. What we have here is when the y equals h, the u is 0, and y equals minus h, so u is 0, right? It looks kind of similar, but it's going to give you the answer for the C1 and C2. So if you plug that in, then u at the y is h. It's going to be h here, and C2. So P, this is basically constant. Then you have a h squared plus a C1h plus a C2. If you plug the y equals minus h, you will see the same term here, except for this one there, and those are 0. So we have a equation C1h plus C2 equals 0, and the minus C1h equal plus C2 equals 0. That means we have to set the C1 equals 0, otherwise it's not solvable, right? Then from here, we can just set C1 equals 0, then C2 is automatically came out of this expression, which is minus 2 mu h squared over 2 mu dp dx here. Then you can just plug that into the u. So basically, if I just write down the organized one, that's going to 1 over 2 mu p dx. Then you have y squared minus h squared. So this is the parabolic equation. So the velocity profile between the fixed plates. Two plates. Okay, so you have a pressure drop, which is pressure gradients in the equation here. And the mu is there. This is characteristics of the flow. Then the y squared, which is location of the flow. Then minus h, which is the characteristic of the geometry. So if you know the pressure gradient, you can find the velocity at the certain location, or if you know the velocity, you can find the pressure gradient, so on. So when you have an expression between the velocity and the pressure gradient, then you can just do a bunch of other things too. So first, the volume rate flow. So in this case, we are actually having the 2D dimensional, geometry here. So it's going to be not Q, it's going to be Q over the, I'll say just the width. It's going to be in the X direction, which is the axis through the screen here. Then we can just use the notation of a Q. And it's as simple as the integrate from the bottom to the top for the velocity, right? That's going to be minus h. Then you have an expression of the u now, so I'll just put the u, and it's integral with respect to the y-axis. Okay, so this is, let me just say, per unit it the z axis. So then you can just put this expression u into the integral. Then it's going to be just you know, the first term is going to be the answer. Then you have just put the constant here, g x. Then this term goes to 3y cubed minus h squared ny. Then you have a range between the minus h to the h. Then when you just plug that in, you will have the minus 2h cubed over 3 mu dp dx. Okay, this is going to be the one you'll find as a volume rate flow. Something strange? Can you have a minus sign here? Do you think it's a right one here? Yes. So if you look at the flow within the pipe, no, two plates, in this case. Let's say flow is going on here, parabolic, more realistically. So then you think about this as inlet and outlet. Then if I have a pressure 1 and pressure 2 there and measure it, if it's driven by the pressure, then you have to have a larger pressure. in the inlet and the lower pressure at the outlet, right? Then if you just think about the gradients of the pressure into the x-axis, then this term is going to be the negative value. So if you know the pressure gradient from to the x-axis here, then it's going to be the positive volume flow rate, right? Okay, so simply you can also change the expression here. Then let's say we have a delta P, it's a larger pressure minus lower pressure. Then say the distance between the 2 points, either inlet and outlet or the 2 arbitrary points you choose within the flow, say L. Then delta X is L. Then it's going to be simply you can just use the expression instead of a negative with the negative sign, 2h cubed over 3 mu, then delta P over L. So you can use this expression for the volume flow rate, the volume rate flow. All right. So next thing is a mean velocity. Mean. So when you're looking for a averaged velocity within the flow, the expression I used the U dot bar there, but it's going to be same as the expression of the vector. So let's just use a U mean here. And it's simply just a volume flow rate over the area. What? Oh, this one? Oh, yeah. The mean. Yeah, I'm not a good writer. Sorry about that. Just let me know. All right, then it's going to Q over A. So then simply you can just divide by the area. In this case, actually, the area is the 2D. So is this 2H. So everything is per unit width in z-axis. So the same as a Q in the 2H. Then if you just divide by the 2H, it's going to be simply, just let's use this expression, then H squared over 3 mu delta P L. The next thing is going to be max velocity. So we have a parabolic expression for the velocity profile. Then which location will we get the maximum velocity here? Of course, in the along the center line, right? So along the center line, we'll see that y is going to be 0. So in the equation here, when you put the y equals 0, it's going to be the highest number absolute value from the minus h squared, of course, but the dp over dx is going to be negative, so it's going to be the max number. So simply just u max is going to be when you plug the y equals 0, then expression is going to be 1 over 2 mu d. Let's just write now dp dx and minus h squared. But then you can just simply, this is 2 mu express this with the mean velocity, then it's going to be what? This 2 over 3 over 2 um. So when you have a mean velocity, then the maximum velocity is going to be 1.5 times of the mean velocity. Okay, so that's the relations between the mean velocity and the max velocity. Anyway, so if you have an expression for the velocity profile, you can just simply find those values if you need to. The last thing is the pressure distribution, the pressure variation. So it's from the here we left the expression equation from the y direction, the p equals minus rho gy plus f1x, so which is from the differential relationship over dp over dy equals minus rho g. And from here we know the p is simply, you can say rho gy plus f unknown function in terms of x. Then we actually can now know it's a pressure gradient, because when you take the partial derivative with respect to x, it was the the dp over dx and x, so it's the same, but we can just replace it with the dp over dx and x. That's the same thing. And we can just leave the constant term at the end. And that is actually, when you just think about the x-axis and p pressure, the pressure gradient is going to be linearly decreased here. So let's say this is, we have an initial point at p naught. Then this is dp. And if I set up the initial point at the p naught is a constant, so that's the reference point. Then we call just the reference pressure at x equals y equals 0. Okay. So you need the boundary condition, of course. You need the initial point, actually the reference pressure, which means something like atmosphere pressure. Then if it's given, you can just write it. If not, you can just set it up as a P naught, which is just simply the pressure at the room temperature here. Then you can just find the pressure gradient or the absolute pressure based on the situation. Sometimes we can also say this is the call is a plain version. Boisse's law flow. Because we are going to find the equation for the just C. Going to find the similar equations from the circular pipe today, and it is actually we have to take into account the cylindrical shape of the pipe. But this is actually infinite plates from the bottom to the top. So you can think of the 2D version of the circular pipe, but actually the expression is a little bit different. So. Okay, let's just quickly stop by the example problem, one of the problem in the textbook, the number 72. So the two fixed horizontal parallel plates, so those are the same setup that we have in the previous page, are spaced 0.4 inch viscous liquid So mu viscosity is given. And the SG, what is SG? The specific gravity is given. So it's based on the water density. The flows between the plates with the mean velocity. So mean velocity is given. So you can think about the expression of the mean velocity. The flow is laminar, right? That is actually important. Determine the pressure drop per unit length in the direction of the flow. What is the maximum velocity? Cool. Okay, so let's just solve this one first. The pressure drop per unit length in the direction of the flow. So it's going to be just the pressure drop over the L, right? That's what we are looking for. Then the number we have in this problem is the mean velocity. So you can just look up what's the mean velocity from the previous flow. Then it was h squared over 3 mu delta p over L. Then you can just plug the numbers here. What do you have? So it's a spaced 0.4. So it's going to be what? We set up the axis in the middle of the pipe, the middle of the spacing. So the 0.2 is going to be the one. So when you plug the in, h is 0.2 inch, then you have to convert it into the feet, right? So everything is feet and second and pound. So when you do it, it's going to 0.1667 feet. Then rho is going to be what? Rho H2O multiplied with the 0.9. That's a specific gravity. So it's going to be 1.9 1.940 slug per feet. Here. You don't need this time. So the mean velocity is 0.5 feet per second. It's going to be 0.01667 square. Then 3, and the mu is what? The 8 multiply 10 to the minus 3. And you have a delta P over L. So delta P over L is going to be 43.18 pound per feet square. Of course, this is per unit wood. In the z-axis. So actually, you're gonna check the units. Then it's actually going to be pound per feet square, and you need 1 feet more because it was a per unit based. Then the last one is maximum velocity u max. So it was simply what? 1.5 times the mean velocity. So it's just simply 1.75 feet per second. Okay. So when you have those exact solution from the specific flow field case, this is one of the simple one. Then you can just use the exact solution to solve for any flow field based on the similar setup here. Okay. So you're gonna go through some of them more. Actually, another one is a quite flow, but I'll just jump into the one in the circular tube first because we're gonna deal with this equation tomorrow in the lab. All right, Now it's considered a steady, incompressible laminar flow. So everything's same as before through the horizontal circular tube. So we have a little bit different setup with the radius r. So we call this type of flow as a Hagen-Buzz-Weiss law or Hagen-Buzz-Zay's law of Zay's flow. So, or just simply the Buzz-Zay's flow. So those are all same name. And this is really the popular one because we just flowed all the waters in the pipe, and this equation can be applied. This exact solution can be applied to any water flow or the Newtonian flows field as long as it's a laminar flow. Okay. Then this is, we are dealing with the circular shape of the tube, so it's better to use a cylindrical coordinate system. That's why I just copied all the Navier-Stokes equation here. R, theta, z. Of course, if it's problems in the quizzes or the exam, you're given the equation. So don't worry about that. You don't have to memorize it. All right, just take a look at some geometry here. We have a circular pipe, and the axis of the z is directed along to the actual direction of the pipe. Of course, the radial direction is to the radius, and the theta is given from some reference point. Then we have a gravitational force, and the velocity is flows across through the streamline in the pipe. So of course, it's going to be the function of y in this case. But let me just write down another one. So first of all, what I'm going to do is actually find the gravitational force. So gravitational is simply, you can just define in the vector form was a minus g, in this case j. That was all. But actually we are using the r theta z axis in this case, so we have to convert it into the r and theta axis, which is transverse axis. In the circle here, let's say this is r, the unit vector. Let's use the same vector here. And this is the theta. So this is the unit vector of the E theta. Let's think about the one of the elements here. The G is there. Then you can think about the line of action here. The theta here is the same. So the G can be now expressed with the minus G sine theta along the E minus G cosine theta in the transverse direction. Okay? So that's why we usually keep the GXYZ, and also in this case a GR theta Z, because you don't know whether you have a gravitational force in that directions. It's based on the orientation of the coordinate system, of course. Okay, then let's go through the assumptions now. Yeah, we know it's a steady state, so can I just make a little bit of space here? Oh, nope. Okay. Just let's write down. So steady state, whenever you have a d dt, it's going to be 0. The incompressible, rho is constant. The laminar flow, of course, the horizontal circular, yes. The radius r, all right. Then let's go into the equation now. So we have the flows in the z-axis, therefore Vz is Vz of some function, but the Vr and the V theta is going to be 0, okay? Because it's a fully developed and the steady state. There's no change in the velocity along the z-axis too. So whenever you have a Vz over V is going to be 0, too. And now looking at the velocity here, Vz is going to be the function of what? Previously, it was a function of y. In this case, it's now a function of r. Why not for the theta? Okay, this is axisymmetric geometry, so it's not going to be the function of a theta. Also, you can say axisymmetric. All right, those are the one we know of. Then just let's apply those assumptions here. So this is continuity. Of course, you can start with the linear momentum equation. Yeah, for sure. But always it's good to start with the continuity. So you can just check. At least you can find whether it's some function of in terms of x, y, z, or in this case, either a function of r, theta, z. All right. Of course, you can just remove here. Yes. Oh. Axisymmetric. Axisymmetric. So it's symmetric to the actual direction. So there's no variation along the transverse direction, which is along the theta. So either theta equals 0, theta equals pi, theta equals 2 pi, theta equals pi over 4. So all the values of the profile should be same. So we have VR and the V theta is going to be 0. So this term goes to 0. We know VZ is going to be some function is at 0. So we know it's going to be the function of R. That's what we already said here. Then it's time for the Navier-Stokes equation. Of course, yeah. Incompressible Newtonian fluid, we can always use the Navier-Stokes equation. Then this is just a little bit different. We have extra terms because of the effects of the cylindrical coordinate system, but we can just still apply the same assumptions. All right, first of all, VR and V theta equals 0. So we can just take out all the terms here. Let's use a different color. And V theta is 0, so this is all gone. Gone. So VZ, okay, VEZ is available, but it's a function of R. So we can just remove it. Here we have a V theta, so go VZ over DZ, so this is 0, 2. And here is a pressure. All right, pressure gradients along the R axis and theta axis and Z axis. Those are going to be kept in this equation. Then G, so we have a GR and G theta components. So I'm going to just keep these two, and not this one. That's going to be 0. And all the R axis down, what you have here is a VR over VR over V theta over VR over. So eventually you're gonna just remove all terms here. All right, so we pretty much just remove all of them. And the theta direction, we have a V theta, VR, V theta. Okay, at least we just remove all here. And V theta is also 0, so it's a 0, 2. Nothing is out there. All right, so finally, we have here. It was, oh, there's a VR here. So sorry about that. I thought it was a VZ. So VR, V theta equals 0. So here we have a VZ, so gotta be careful. So VZ is a function of R. So let's take a look. VZ over R, so it's going to be non-zero or constant at least. So you can just keep it. It's going to be the another derivative with respect to r. So it can be a constant or a function and r there. So we have to keep this term. And Vz over d theta, so it's going to be 0 because it's not the function of theta. And it's not the function of a z, so we can just remove it here. Okay. So a few terms left now. Here, there, here, there, here, and there. Okay. So from first expression, dp over dr plus rho g r. So let's just plug that in. So gr was a minus sign g, so it was minus rho g sine theta. Then you can just take integral over to the both sides with respect to r, which is dp is minus rho g sine theta d. I'll just use the d actually. Oh, I just leave it there. I just change the d because it's all about the p. So then we have the expression that says p equals minus rho g r. Of course, it's all about the r and sine theta. Then plus, I don't know, the known function, let's say just prime, and it's going to be theta and z. Okay, that was the first one. The second one, now we have a minus 1 over r dp d theta plus rho g theta. It's going to be minus 1 over r dp over d theta minus rho g. Now it's a sine theta equals 0. Sorry about that. Cosine. Yeah. So it's the same. We just take the integral on the right, both sides. Of course, the r should be now to the right side. So it's going to be something like dp is a minus. Let's just use the integral minus rho gr cosine theta d theta. And it says p equals minus rho gr. Same, the integral of the cosine, so it's going to be just a sign without any sign change, and plus a known function in terms of we take the integral over to the theta, so it's r and z. So we have like same expression here for the p. Then it's going to be not about the theta, not about the r. So we at least know the p is rho g r sine theta plus some function of z. We're going to just leave it out there just as is, and we're going to just revisit. And then finally, the third equation along the z-axis, what we have is 0 minus p dz plus mu 1 over r d over dr r dvz dr. Okay, so finally, so the same here. I'm going to just move the pressure gradients to the left side and divide by the mu and move the 1 over r again. It's going to be d over dr. You don't have to do this for the lab reports, by the way. Oh, it's not a report, so you don't have to derive the equation, at least for the lab. I'm doing it. It's going to be mu 1 the dp over dz, and we have r. Okay, now take the integral on the both sides with respect to r. Just one. It's going to be r dvz over dr. Then the 2 mu r squared dp over dz. We have r and r, so you can just remove it unless it's 0. So take the integral again once more on the both sides. Then it says a vz is now 4 mu over r squared. Oh, sorry about that. Constant term, C1. And one more time, the vz here. The first term is going to be just a 4 mu in the r squared dp over dz. Then what's the 1 over r, the integral of the 1 over r? Can you remember the integration? When you integrate some function like 1 over r or 1 over x, it's going to be the natural log. So it is C1 ln r. And we have another constant here. Okay, this is it. This is the velocity profile of the flow in the circular pipe. Now it's time to apply the boundary condition like we did for the infinite plates. What's the boundary condition at this point? What do you have? We have just one boundary condition, right? When the r is large r. This is r. So when the r is large r, which is the radius, then we have always no slip condition. So v z equals 0. We have two unknowns, actually. We need one more boundary condition. That actually comes from the maximum velocity. When you look at the value at the r equals 0, then let's take a look. The vz, so r equals 0, which is a 0, plus a c1 ln 0 plus a c2. I don't know what the number is, but you can definitely say the ln 0. If you look at the graph of the ln, natural log, it looks like this. What does that mean? When you plug the 0 into the natural log, then it's going to be negative infinite. So this one is a negative infinite. Does it make sense? No. So along the center line of the pipe, we have to have the maximum value, maximum velocity of the flow, not the minimum or the infinite number. So it's not a realistic. It's not valid number. So we can set the C1 equals 0 to be practice. And because of that, when you plug the R equals large R, capital R, the VG can be found. VZ equals find VZ at R equals R going to be 0. And you plug in, it's R squared over 4 mu dP dz plus C2. So C2 is basically minus capital R square for mu dp over dz. So let's just write down this solution now. You will have a bz 1/4 mu dp over dx. Then now you just have a r squared minus capital R square. Velocity profile. Velocity now distribution at any cross section. Okay, so it's same now. We're gonna just looking at the volume rate of the flow and mean velocity, max velocity. So you can just take the integral over to the pipe. So, it's going to be this integral over to the 0 to the capital R, which is the end of the radius, then Vz, then you need a 2 pi R, which is the circumference of the differential element, and it's going to be dr. So basically just dr. And from here to there. Okay, so it's going to be this large Q. When you plug the Vz into the integral, and it's going to be 2 pi for mu. Still same the temperature pressure distribution there. The integral r squared minus r 0 to the r dr. Then let me just give you the final answer. Minus pi there. So it's going to be the volume flow rate of the pipe. Now you might check this with the one we have for the infinite plates. It's going to be a little bit different. And again, we can also use the pressure drop instead of the pressure gradient. So we can just knock out the negative sign. Then we can have the expression. Same here, but positive value with the delta P over L. So L is going to be the 2 points you set within the flow. All right, so now, yes, sir.
When you're writing dp dx, do you mean dp dz in this case?
Oh yeah, it's a dz.
Okay.
Yeah, it was a dz up there. Okay. So the next one is maximum velocity. Of course, maximum velocity is the Vz at the z r equals 0. So you will have the same process to get this. And also, you can use the expression with the pressure drop, all square over 4 mu delta P over L. Okay. The mean velocity is what? It's going to be just a Q over A, right? We just averaged across the area. So basically just a Q divided by the pi r square. So you will have the r square over 8 mu. With the pressure drop, I'll just skip pressure drop. It's much easier to look at it here. Okay, again, we have a mean velocity, so let's take a look at the max velocity. It was a 3/2 of the mean velocity for the infinite plates, but now actually now 2/2 of the mean velocity in the flow. So we have a little bit different numbers, right? Okay, it's time to finish it. So I'll just pick up this to show you how we can find the dimensionless form of the equation. Then you can just apply those equations to find some of the valuable information from your experiments. So just take a look at these equations again, the volume rate of the flow and the maximum velocity and the velocity across the pipe. We're going to use this equation to see how we can find the actual velocity within the pipe. Okay, I'll see you tomorrow over Teams, completely online. I'll just set up another appointment for the lab for each session. All right. Hold on. What's that? VM is it's a mean. Yeah. So we usually like M. This is a mean velocity. Now max is just we call max. All right. Thank you guys. I'll see you tomorrow and on Thursday, the Friday.